Imagine sharing a pizza with 10 friends. You get a small slice. Now share it with 100. Now 1,000,000. As the group grows, your individual share approaches zero. In calculus, we write this behavior using limits. As the denominator of the fraction gets infinitely large, while the numerator stays constant, the value of the entire expression approaches zero. This behavior applies to any constant divided by x raised to a positive power. As x heads toward infinity, the fraction vanishes, becoming a zero term in our equation. To evaluate limits for complex rational functions, we use a specific algebraic maneuver. Identify the highest power of x in the denominator and divide every single term in the function by it. This transforms a messy polynomial into a string of simple fractions. Most of these will vanish as x grows, leaving behind only the terms that dictate the function's final behavior. Let's apply this to a function where the highest power of x is the same on top and bottom. Check the denominator. The highest power is x to the first. Divide every term in the numerator and denominator by it. In the leading terms, the variables cancel, leaving just the coefficients, 3 on top, 2 on the bottom. Next, look at the remaining fractions. Any constant over x goes to 0 as x gets infinitely large, so both -1 over x and 5 over x disappear. This chart shows the function's graph. Our calculation resulted in 3 halves, and visually, you can see the curve leveling out precisely at the horizontal line y equals 3 halves. What happens if the denominator is heavier? In this function, the highest power on top is x squared, but the denominator has an x cubed. We stick to the rule. Divide every term by the denominator's highest power, x cubed, regardless of the numerator. Distributing x cubed leaves fractions for almost every term, except the leading term on the bottom, which simplifies to 4. Taking the limit, every term with an x in its denominator vanishes. The numerator collapses to 0, and the denominator becomes 4. 0 divided by 4 is 0. This chart shows how the function behaves. Because the denominator outpaces the numerator as x grows, the limit is 0, pulling the ends of the curve toward the x-axis. Now consider a top-heavy function. Pause the video and try dividing every term by the denominator's highest power. Dividing everything by x simplifies the expression to 3x plus 4 all over 1 plus 2 over x. As x heads toward infinity, the 2 over x vanishes, leaving a 1 on the bottom. However, the 3x on top continues to grow without bound, leading to a limit of infinity. When checking the limit toward negative infinity, pay attention to the remaining x terms. Their signs will determine if the function shoots up toward positive infinity or plunges toward negative infinity. This chart demonstrates the result. Because the function is top-heavy, it never levels off. Instead, the outputs shoot straight off the coordinate plane. You might notice that top-heavy functions don't just move randomly. They often follow a nearly straight path. This happens when the numerator's degree is exactly 1 higher than the denominator's. This chart shows the curve hugging a slanted line. For large values of x, the function acts like a linear equation, creating what we call an oblique asymptote. Identifying these patterns provides the structural guidance needed to accurately sketch functions that grow without bound. We can consolidate these behaviors into a quick reference for evaluating rational limits at a glance. First, if the highest degrees match, the limit is the ratio of their leading coefficients. Second, if the denominator has the higher degree, the limit is always 0. And third, if the numerator has the higher degree, the limit will be positive or negative infinity. These shortcuts allow you to verify your work instantly, but remember the underlying algebraic division. It is the process that proves why these end behaviors exist.